one. The first time you're introduced to the log is back when you learn exponential functions, because logs are the inverse to exponential function. Okay, so a log is the inverse to an exponential function. So think about inverse operations like addition and subtraction are inverses of each other. Multiplication and division are inverses of each other. A square and a square root, a quadratic and a square root function are inverses of each other. So inverses undo each other. So a log can undo something exponential and vice versa. Okay. The other thing that I really stress about logs is to understand that a log is a man-made thing, right? Some mathematician someday decided that they would use logarithm to describe this thing that's happening. Okay? A log is just an exponent. Okay? The answer to a logarithmic expression, whatever it's equal to, that's your exponent. So in this expression, or this equation, log base 4 of 16 equals 2, the answer to the log, so the log is over here, right? Here's the whole log expression. The answer is the exponent. This stuff right here is just asking the question, what exponent do I need for base 4 to get 16? Can you see why a mathematician might come up with a shorter way to write that question? Log base 4 of 16. If we just all agree that that's asking about an exponent, then we don't have to write the whole question. What exponent do I need for a base of 4 to get 16? I just write log base 4 of 16, and you guys know it's asking about an exponent. So I have 3 equations here, and I just want to kind of rewrite them in exponential form to kind of reinforce what a log is, right? So we kind of already know this one, the top one. The base is 4, the exponent is 2, and it's saying it equals 16. Do you agree with that statement, 4 squared equals 16? Yes, when you rewrite it, it should still make sense. Okay. So log base 3 of 81 equals 4. You would rewrite that as 3 to the 4th. 3 is the base, so the base of the log is the same as the base to the exponent. The answer to the log is the exponent, so we put the 4 on, and it equals 81. Yeah, that makes sense. Okay. The last one that I have down at the bottom, just to kind of reconfirm some things we know about exponents, I have log base 9 of 3 equals 1/2. So that's saying 9 to the 1/2 equals 3. Now, 9 to the 1/2 does not mean 9 times 1/2, 4.5. I would just write multiplication if that's what I wanted to do. Remember, when you have a fraction in your exponent, that's like taking a root. So the root is in your denominator of your fraction. If it was raised to the 1/3, it would be a cube root. If it was raised to the 1/4, it would be a 4th root. Since it's raised to the 1/2, it's a square root. Do you agree that the square root of 9 is 3? Yeah, so this is a true statement. So real quickly with your groups, use your brain power, not your calculators here. Can you tell me can you evaluate the logarithmic expression log base 5 of 1/25? So remember, what is a log? A log is a simple way to ask this question over here. What is the exponent you need for that base to get that number? Okay, so you and your group are thinking about what exponent do you need for a base of 5 to get 1/25? is my thought bubble, so you can see inside my brain. What I think of when I see this expression is I think about it in exponential form. I don't know what the answer is right now, and the answer would be my exponent. So I put like a question mark or an X up there. And I'm saying 5 to what exponent equals 1 over 25. And that makes it easier. If it's going from an integer of 5 to a fraction, what kind of exponent do you have to have? It has to be a negative because that's going to flip it. And then if I flip it, it would just become 1 over 5, but I need it to be 1 over 25, so it must have had a power of 2. So it must be negative 2 is my answer. So 5 to the negative 2 will flip and be 1 over 5 squared, which is 1 over 25. And you can do that without a calculator, right? Okay, so that'll be helpful because we're going to be graphing, and you'll need to be able to like think about logs or evaluate logs when you're graphing. So you can get some points. Okay, before we get into graphing, we have a couple of quick slides here. First of all, definition of a log function is just the inverse to the exponential function. So yesterday we had y equals a to the x. Now we're going to say y equals log base a of x. So they have the same base a. Okay, one is exponential and one is logarithmic. Down below I put in quotes. I always like to do this for people so that they know what I'm saying. So if it helps you to write that down, write it down. I know when I'm in a math class, I always write down what they're saying because when I see that notation, I want to be able to read that. Okay, so that says log base a of x. Well, this is really just the inverse to the exponential from yesterday, so the things must be true about a that were true yesterday. A can't be negative. So never will you have a negative base in a log. Okay. And it also can't be 0. Okay. And then a does not equal 1. Okay, that's not a very interesting log. The last statement, the last bullet point that I have right here, this can be really helpful for like rewriting. Okay, so it's going from log to exponent form, but I could really look at it either way, and I could take something in exponential form and write it as a log. Okay, so I can go in and out of either form. So that's what we were practicing on the previous slide with the numbered equations. Y equals log base a of x, but that implies that a to the y equals x, so y is the exponent. Okay, now I have 4 properties I'm going to put on the screen. I'm going to give you some time to jot them down in your notebook. And then I'm going to ask you and your group members to kind of think through. Can you figure out what goes in the blank? I haven't finished the properties. So I'll give you some time just to write them down. And then I'm going to ask you to discuss with your group. See if you can come up with an answer. So they look like log base a of 1 equals log base a of a equals and then the last two. One is called the inverse property, which you learned last year in Algebra 2. But you can also just think about it and figure out what goes in the blank. And then one is the one-to-one property for logs. Okay, so once you get them jotted down, now you kind of like throw out some ideas with your group members. What is the thing that goes in the blank? So think about what you know about logs and how they work. Rewrite them if you need to. What goes in the blank?
If we rewrite it, it would be a y equals 1 for the base of a. That's 0.
It would just be x, right?
Isn't it everything? No. And it also. Never. Base of a. First one's 0. And the second one be 1.
Okay, let's come together. Log base A of 1 equals what value? 0. Okay, I'm going to add to this a little because statement. So BC for me means because. Because if I write that in exponential form, that says a to the 0 equals 1. And that's the 0 exponent property, right? Anything to the 0 is equal to 1. So that makes sense. The log base A of A is always equal to 1. Okay? Because you're saying a to the first equals a, and that would be true. Okay. So did anybody groups figure out what log base A of a to the x was? What's that? I'm sorry, I couldn't hear. X, yeah. I mean, you could use the same reasoning that I used above here, right? What's the base? A. And before we didn't have an answer, so I'm going to put a little question mark up there, right? So we're looking for what exponent we would use for A so that it equals a to the x. Well, the only thing that's going to work is x. And you could also use the idea that this is an inverse property and inverses undo each other. So if you have a log base A of an exponential a to the x, they're undoing each other and you just get x. So what do you suppose a to the log, oh sorry, I moved this so my a got moved. What do you suppose the log base, or a to the log base a of x is? Don't think too hard. Lexi says x. Yes, they're going to undo each other. Inverse. Undo. Everything goes away. It's just equal to x. So if I have 5 to the log base 5 of x, it just equals x. Or log base 5, or 5 to the log base 5 of xyz. It equals xyz, whatever came behind. Okay, so they just cancel each other out. And the last one, log base a of x equals log base a of y if and only if what is true? X equals y. That's your one-to-one property, right? And doesn't that make sense? If they have the same base, you have to have the same thing behind the log, otherwise you're going to get a different answer. Okay, so you can use that one-to-one property as well. Okay, so I'm going to put stars next to the first two properties. That I'm always going to use those two properties in my table. They'll be really easy to evaluate if I put in the right values for x into my log function. And so the values that I'm always going to be putting in for x are going to be the 1 and the a, which is just the base. So I'll always put in 1 and always put in the base to my x, and I'll always get out the same two numbers, 0 and 1. Okay, so let's look at a graph. We're going to do graph y equals log base 2 of x. Now this is one of the basic ones where I don't have any extra numbers. I'm going to do another graph where I add some extra numbers in with the log. Okay, but this would be what I would call like one of the parent graphs. It's super easy. I don't have any transformations. See ya. So I just said I would use those properties of logs to pick the same numbers always for my x coordinates. And I'm going to use always for x, because that's what I'm putting into the log. I'm always going to put in a 1, and I'm always going to put in the base, which will change. In this case, the base is 2. So if you need to, off in the margins, why did I pick 1 and 2? I always put in 1, and I always put in the base. Always put in 1, always put in the base. Now, I can, work it out, right? So I could say, well, if I'm putting 1 in for x, I'm saying y equals log base 2 of 1. And I'm thinking about 2 to what exponent equals 1? And the answer is 0. But we already knew that because that's the property. And I could do the same thing for 2. Y equals the log base 2 of 2. Well, that's saying 2 to what exponent equals 2? And the answer is 1. So when you put in the base, you'll always get 1 out. When you put in a 1, you'll always get 0 out. That's always the exponent. So these are going to be my 2 points. Now, if you wanted to, you could pick or try to find other values that would work out. So think about 2 to an exponent equals something else nice. What would be a nice x that I could also put in if I wanted to? Brendan, you're saying 4. Okay. 4 wouldn't be a bad choice. I don't always do this, but I could put in 4 because I'll be able to evaluate. Y equals log base 2 of 4 is asking the question 2 to what exponent equals 4, and the answer is 2. Can you think of a number that you would put in that's less than 1 that would work out? Y equals the log base 2 of 1/2. If I wanted more points, and you don't have to do this for all of them, okay? But if I put in 1/2 for x, then aren't we asking the question 2 to what exponent equals 1/2? And you guys would tell me -1. Okay, so I'm going to do that on this first one so we can see a better shape. But I am going to box these two, those are really the only 2 I ever do going forward. Because I kind of will figure out what the shape is and then I'll be good to go. Okay, so let's plot those 4 points that we have. 1/2 -1, 1 0, and 2 1, and then we also have 4 2. Something interesting that you should be aware of about logs, and I've mentioned it before way back in chapter 1, but there are some numbers you can't take logs of. Can't take logs of what kind of numbers? Negatives or 0. Okay. So if I put in a negative number, like y equals the log base 2 of -1, then I'm asking the question, 2 to what exponent y equals -1? Well, do exponents ever make things negative? No, we know that negative exponents flip them and make them fractions. So we're never going to get a negative answer. And I also can't do y equals log base 2 of 0. That's asking the question 2 to what exponent equals 0? Will I ever be able to put in an exponent and get 0? No, that's what we talked about yesterday. That's why we have a horizontal asymptote for an exponential function. Because it always flips and you have 1 over something. So we can't do logs of negative numbers or 0. So just as a side note, kind of be aware of that. So never should I ever see, in your table, should you be putting in negatives or 0s in the x's for a parent graph, because you're not going to be able to do it. Well, that means that you have, instead of a horizontal asymptote, we have a vertical asymptote. That at x equals 0, it doesn't work. Okay, we get a vertical asymptote. And that should also make sense knowing what you know about inverses. You're switching x and y. So yesterday we had a horizontal asymptote, y equals a number. When we switch x and y, that's going to turn into x equals a number. Okay, so my vertical asymptote is going to be at x equals 0. And then with these points, I can kind of figure out what's happening. This side must be attracted to that vertical asymptote. I'm just going to run next to the asymptote. And then this side, it sort of reminds me of like a square root function in that it's increasing slowly, but it will be increasing. It doesn't turn around. So don't draw it so it's coming back down. It just continues to go up. You might be able to think of some other values that would be good x's. You could put in 8 and you would get 3. You could put in 16, you would get 4. You could put in 32, you would get 5. Those are the powers of 2. Okay, and so you can see it's gradually going up always. Okay, what would you say for domain? All real numbers? No, 0 to infinity, right? Okay, don't include 0. It's the vertical asymptote. What would you say for range? This time all real numbers. Go negative infinity to positive infinity. And again, that should make sense knowing what you know about inverses. We switch x and y, so we switch domain and range from yesterday as well. On this one, we can see on the graph, where's the x-intercept? 1, 0. Please write the x-intercept as an ordered pair, right? Okay, 1, 0. Is this graph increasing or decreasing? Increasing from left to right. So we could say from negative infinity to infinity, it's increasing. The graphs, just like yesterday, it's an inverse, it's a reflection of the line y equals x. It's never going to turn around. It never goes back down. So it's only increasing from left to right. You should only answer one interval. Questions, concerns about a log? Okay, so I'm going to take this graph, log base 2 of x, I'm going to add an extra number in so that we can talk about transformations and how we might graph. I'm going to graph real quickly log base 2 of x minus 3. Okay. Now remember, this is also happening in the no calculator part of your quiz and your tests. So like yesterday I said, don't like pick numbers and plug it into that whole equation with all those extra numbers because it's hard to keep track of all that without a calculator. I don't want your calculations to be hard in no calculator. So notice, even though I have this x minus 3, in my table, I'm going to leave out the minus 3 and I'm just going to do what I would call the parent graph. So I'm only going to graph log or make up table values for log base 2 of x. So this would be like my parent graph. Now, this is the same parent graph that we did before, but when I get to that parent graph, remember, I'm always going to choose the same 2 values for x. I'm going to choose 1, and I'm going to choose the base. So if the base changes, you'll pick a different number, but I'm going to choose 1 and 2. 1 will always give me 0, and 2 will, or the base will always give me 1. That's the property of exponent that we talked about. And then if I look back up here, what transformation is happening for x minus 3? We're going right 3. So this is really easy. These are easy points for me to get. 1, 0, base 1. Okay. Plot those points. And then move them right 3. So just count out 3 to the right and plot a new point. What else is going to move right 3? The what? The vertical asymptote. I'm sorry, I didn't hear that. Okay, vertical asymptote. So move VA2. Okay, so it used to be at x equals 0. Now it's moving right 3. So it's going to be at x equals 3. And I have less points here, right? I don't have all 4 of those points to help guide me. But I kind of know what the shape of a log graph is now, right? The left side's going to be attracted to the vertical asymptote, so it's going to drop. And this other side is the side that's slowly going to be increasing, okay, as it goes through the different powers. What's your x-intercept for that graph? 4. You can see it on the graph. I'm going to do one here where, like, what if it wasn't on the graph? I'll show you how you can do it algebraically. But it's 4, 0. Of course, the range is negative infinity to infinity. By the shape of the graph, you can see it's going to hit all the y's. And then domain, what would we change about domain? 3 to infinity. Excellent. Okay, so if your vertical asymptote shifts, then you're going to have a shift in domain as well. There's no graph on the other side of 3. So don't include that in your domain. Now, if you only had like a k value instead of an h value, if minus 3 wasn't in parentheses, if it looked like log base 2 of x minus 3 with no parentheses, that would be a down 3. And then your vertical asymptote, I mean, it would technically move down 3, but you're not going to notice a vertical line moving down. So its vertical asymptote would still be at x equals 0. Okay, domain would still be 0 too. Okay, any questions about graphing? This would be increasing from negative infinity to infinity. Anything you want me to clear up? Okay, so like, could you imagine this if instead of moving right 3, I had you move these 2 black dots down 3? Okay, then when I ask about an x-intercept, where would your x-intercept be? You wouldn't know it on the graph. So I'm going to do an example here where I'm going to find the x-intercept without a graph. So I'm not going to graph this whole one. I'm just going to like address the issue of finding an x-intercept. So it looks like f of x equals 2 minus the log base 2 of x minus 1. Okay, what do you know about all x-intercepts? What is always true, Brody? The y value is 0 because they're on the x-axis. So I could just set y equal to 0. Now, we will solve equations in section 3-4 next week on Monday, but you've already solved equations in Algebra 2. So, like, you're basically running reverse PEMDAS. Move this 2 to the other side first by subtraction. Okay, so that's going to be negative 2 equals negative log base 2 of x minus 1. I'd like for my log to be positive, so I'm going to like divide by negative 1 on both sides. If you're okay with this, they both become positives. Okay. And then now I have log base 2 of x minus 1 equals 2. Well, we could do what we were doing in the beginning, which is just rewrite it in exponential form, right? This is base 2. What's your exponent? 2. And that equals the x minus 1. So we moved from log form to exponential form, which, you know, this is kind of nice because you get a little bit of practice with this before next Monday when we solve equations. We're going to solve equations that are much more challenging than that one. Okay, so that's kind of like a little quick review. But that's 4 equals x minus 1, and of course add 1 to both sides, and x equals 5. So it's the x value of 5 that equals 0. So there's my x-intercept. Now, they don't always come out that nice. So, like, you could have one where, like, let's say instead it was log base 2 of x minus 1 equals a negative 2. So, like, what if it wasn't equal to a positive? Then we would rewrite it 2 to the negative 2 equals x minus 1. This one is a fraction of 1/4. And I can do 1 on that side. That's x equals 1 and 1/4. Right? That's reasonable for me to ask you to do. Okay. And then you could say that that's where the x-intercept is. It's a little past 1. So you can mark that on your graph. Okay, now the last thing to make note of that you'll be asked to do on the homework assignment is you'll be asked to do some natural log problems. So these are like the inverse to the e problems, which means that you're going to have to use a calculator. So why don't you just try typing this in your calculators right now before you leave. We've got a few minutes, and just make sure everybody can get a graph that looks similar. We got some of the same values in our table of values. So we're going to do 3 natural log x plus 5. You don't want to use the e, so you're not going to hit the second button anymore. I don't know why this fly won't leave you alone. It was up here by me before. It was. Oh no, there's like a mosquito on the wall. Scaring me. I'll pull up my calculator here and see if I can get it. But you just want to type the natural log button. You don't want to do second e. So can you get the correct answer? Can you see where your vertical asymptote is in your table? Yes. How do you see it? What happens? Okay, you might be looking at the graph. Okay. I'm going to type this in. 3 natural log x plus 5 close parentheses. Yes, okay, so if I graph it, I can see it in the graph. It looks like it's at -5. And then remember, like, to graph this on a quiz or a test, you would still want some nice points. So you could do second graph to get to this table and pick some of these. And then as I scroll up, see, you can tell where your vertical asymptote is. Nothing happens beyond 5 or -5 because then we get zeros and negatives. So I would probably like start at that moment where my vertical asymptote is, pick like 3 or 4 points, plot them, and then I have a graph. Okay. Okay, so your homework assignment is on your Gold sheet. Okay. You're going to have a quiz this Thursday over 3.1 to 3.3. So really be thinking about as you do your homework, especially the graphs. Can you graph it? Can you list characteristics about the graph? The Chapter 2 retake deadline is next Thursday, and the Chapter 3 test is happening next Friday. So all of a sudden, we're going to have another test.